Have you ever wondered what an architect does? Or considered becoming an architect? Or perhaps you are working with one, or plan to become one in the future. Nice to meet you. My name is Jairo Suarez Carrillo, data management engineer. My career spans 50 plus years. I've had the opportunity to work in a wide range of project types: education, retail, telcos, outsourcing companies. Here, I will break down the process architects, where we also determine the degree of utility, performance, and cost of the blockchain application. Welcome, and thanks for joining me. During the next 50 or 20 minutes, we are going to hear terms as analytics, blockchain, databases, data governance, data handling, distribute data management, distribute databases, software architecture, transaction databases. While blockchains enhance the quality of the data by providing a transparent, immutable, and consistent data store, the technology also brings new challenges. From data management perspective, I analyze blockchains from the viewpoint of a developer to highlight the important concepts and considerations when incorporating a blockchain into the larger software system as data store. First, we identify the common architectural layers of a typical software system with data stores and conceptualize each layer in a blockchain's terms. Secondly, we examine the placement and flow of data in a blockchain-based applications. Third, we explore data administration aspects for blockchain, especially as distributed data store. Fourth, we discuss the analytics of the blockchain's data and trustable data analytics enabled by blockchain. Lastly, we examine the data governance issues in a blockchain in terms of privacy and quality assurance. An engineer in a lab in Geneva in 1980s observed how scientists struggled to share their work with each other. Information was on computers around the world, but it was hard to get to it. So he created the World Wide Web. And this has given us all new superpowers. We can pass data around the world with ease, and it sparked a global wave of creativity, innovation, and collaboration. I am going to help you to describe in a common language what blockchains accomplish. To get there, let's compare it with something that we know well, the web. What did the web accomplish? It is hard to answer. The web does so many things, and it bears this business model that have completely transformed our lives. But the big picture, put very simple, the web made it easier, faster, and cheaper to communicate the data. In just few years, besides the initial cryptocurrency applications, the foundation of the blockchain technology are now being utilized for many other classes of applications, such as asset management, medical health, finance, and insurance, to name few. From the viewpoint of such applications, blockchains enhance the quality of the data through transparency, immutability, and consistency. However, the exact nature of the blockchains that gives these benefits also brings new challenges from data management perspective. For example, in terms of the blockchains as data store and processing network, following issues open could be observed. The data models used in a blockchain vary from key value to document stores and are usually combined with off-chain data stores. Therefore, searching and retrieving heterogeneous data in a blockchain-based systems takes handcrafted and adult programming efforts, unlike the abstract and declarative queries techniques in a conventional databases. Considering the increasing demand of the blockchain data analytic at the scale, understanding how to efficiently access, integrate, and analyze the data in this heterogeneous environment is essential. The volume of data that the blockchain network stores and manages will only grow with time. However, many contemporary implementations show low throughput, low scalability, and high latency. A good understanding of blockchains in terms of how data are stored and managed can help application developers and database administrators to get better design and control a large software system where a blockchain and auxiliary database may coexist. Blockchain can provide trustworthy and neutral data storage platform from a large software system that use blockchain as component. Trust and neutrality come from the following properties, which are resulting from the unique design of the ledger structure, the network consensus, the consensus protocol, and cryptographic mechanisms that it uses. Transparency. Data stored on a blockchain are accessible to all participants within the blockchain network. The data on public blockchains is visible to everyone on the internet. Immutability. Due to the distributed consensus process, once data are appended to the blockchain, they cannot be changed or deleted. However, immutability might be probabilistic for blockchains using certain consensus protocols. All the transactions in the blockchain network are stored as immutable records. These immutable records become in a public audit trail for regulatory purposes. Consistency. Distribute consensus and immutability ensure all committed data are visible to all future data manipulations, establishing in a single truth across the blockchain network. Equal rights. Due to this intermediation, every participant in the network has the same rights to manipulate and access the blockchain. With different consensus protocols, these rights might be weighted by computation power or is taken owner by the participant. And something that I forgot to mention, availability. Every participant within the blockchain network might host a full replica of the blockchain's data. From the software architecture perspective, every design decision of the system is a trade-off among multiple properties. Likewise, confidentiality and performance are two main criticisms arising from a design of the blockchain. I define a conceptual architecture of a software system detailing blockchains and its data store layer. Broadly, 3 different types of applications utilize blockchain technology and its core. First, currency, like Bitcoin or micropayments. Second, contracts, like automated insurance processes based in agreed terms. Asset management, land registry, and digital corpus is the best example. Just like in a conventional database-based application, the conceptual data model underpinning a blockchain-based application needs to be mapped to the logical and physical levels of the data stored to persist. On the right, I show you a conventional database to highlight the interpretation on how blockchain's data store can be explained from a conventional view of database-based application architecture. In the following, I'm going to present my view of a blockchain's data store as 4 layers, namely logical data store, physical data store, data access, and data processing layer. It is noted that while the layers are stacked in the order that you see in, we present the layers in a different order to simplify this discussion. Logical data layer. From database developers' viewpoint, this level concretizes a conceptual model of data to materialize forms such as relational tables. So, that application can interact with data store. For example, issuing queries to a database. It is well-defined area of programming in the conventional data applications, and most programming constructs support this layer in a standardized way. Example, SQL over relational tables with JDBC in Java. Assets. Assets include both digital assets like cryptocurrency and digitalized traditional assets, such as stocks or titles, which blockchains track the ownership. Smart contracts. Another primary construct in this layer is a smart contract. Smart contract is a set of executable instructions that are activated in response to a message. Physical data layer. A conventional view of a physical data store will be involved in understanding different index structures. For example, B-tree and hash table, which are highly optimized for searching and retrieving data items. In this section, we examine in what physical forms the blockchain's data are represented and their implication on reading and writing. We see data in this level in 3 tiers, namely transactions, blocks, and the layer. A selected set of valid transactions form a block, while a set of blocks that satisfy the consensus protocols is included in the layer. The term transaction in blockchains can mean different things depending on the context. It could refer to the operation that manipulates the data stored on a blockchain, as well as data structure that store the parameters used by the operation. To differentiate the 2 usages, here we are use the term transaction record to mean the data structure. Transaction records. A transaction record holds both the parameters and results of the blockchain's data operations, performing on the assets and smart contracts. Typical operations are creating new accounts, exchanging assets, or executing smart contracts. An essential characteristic of a transaction record is, once chosen to be included in a block, the record is permanently stored in the block, achieving immutability. Most blockchains also persistently store the failed transactions. This is because of the blockchain's roots to the financial sector, where every data record in a blockchain is a financial transaction requiring utmost transparency. As the blockchain transaction records are immutable, the only way to correct any mistakes is to issue a reverse transaction. Each transaction record has a unique identifier and stored in a key value pair within the block. Block. Every block contains a list of transaction records, might be empty if the blocks are built periodically, Therefore, the exact content and structure of a block are affected by the transaction records it contains an implementation of the blockchain. For example, the transaction record in a Bitcoin or Hyperledger block are structured in a Merkle tree. Moreover, a block can maintain other data structures such as the global state. Merkle trees are typically implemented as binary trees. You can see in the following image. However, a Merkle tree can be created as any array trees with any children per node. In various distributed and peer-to-peer systems, data verification is very important. This is because the same data exists in multiple locations. If a piece of data is changing in one location, it is important that data change everywhere. Data verification is used to make sure that data is the same everywhere. However, it is time to consuming and computationally expensive to check totally of each file whenever the system wants to verify data. So, this is why Merkle trees are used. Instead of sending an entire file over the network, we just send a hash file to see if it matches. The protocol goes like this. Computer A sent a hash of the file to the computer fee. Computer B checks the hash against the root of the Merkle tree. If no difference, we are done. Otherwise, we need to go further. What happens if something is wrong with the file on computer B? Then, computer B will request the root of the two subtrees of that hash. Computer A creates the necessary hashes and sends them back to computer B. Repeat steps 4 and 5 until you have found the data blocks that are inconsistent. It is possible to find one more data block that is wrong because might be more one error in the data. Next, I'm going to focus on operational aspects of the blockchains to ensure it is deployed and maintained to achieve the desired performance, security, privacy, and reliability goals of the application. Blockchain administration is a new domain, and the best practices are yet to be identified. While our blockchains include a unique set of configuration and management challenges, I do believe this task could be well introduced into the job role of database administrator. The extent of involvement of the database administrator in managing blockchains depends on the mode of the hosting and the chosen blockchain platform. If blockchains is public, the administrator's key role will be provide connectivity to the blockchain and explore the either installing a blockchain client via public API service. Services such as Infura or Ether Cluster provide API authentication and pay-as-you-go model to reach public blockchains. Data management engineers need to monitor both the blockchain's performance, throughput, and latency, and resource utilization to fine-tune the parameters such as memory pool size, block size, and hash rate. As the ledger is fully replicated across multiple nodes, unless the blockchain is configured to prune all blocks to enhance the performance, storage, and cost efficiency. The administrator might also need to initiate software updates as soft forks to fix vulnerabilities in the blockchain's platform, enhance the performance, and benefit from new features. In a rare case, hard forks are required to introduce significant functional changes, correct data errors, or recover after a severe attack. The real value of data can be utilized only when they are analyzed to acquire actionable insights. In this regard, to many modern organizations with fast-growing data being equipped with effective data analytics capabilities, it is vital to make major decisions and stay competitive. Blockchain plays two distinct roles in data analytics. First, the data stored in a blockchain and blockchain network themselves provide a rich source of information. Second, blockchains can enable trusted data analytics environments for multi-party data sharing by adding the element of assurance into the data and derived analytic models. Data visualization. In the context of the blockchain-based system, data visualization is essential to illustrate the behavior of the system because a blockchain is highly dynamic with nodes connecting and disconnecting all the time. Several online tools visualize different aspects of the blockchain. For example, BitNodes and EtherNodes visualize geographical distribution of Bitcoin and Ethereum networks. Daily blockchains and Interact visualize transactions on Bitcoin. Data mining. The immutable data stored on a blockchain is a public data set accessible to anyone within the network. Hence, can be used to analyze the historical behavior of the system. Besides the visualization technique introduced earlier, the data stored on a public blockchain like Bitcoin and Ethereum have been mined for different purposes. Governance refers to the comprehensive control, including processes, policies, and structures, which could be applied, for example, IT or data assets to support right decisions making in organizations. It's a new technology that breaks many conventional norms, like removing a central mediator. Blockchains have not yet come to terms with many areas of governance. Take cryptocurrencies, for instance. They are essentially tokens issued within the blockchain platform. Example, Bitcoin or Ethereum. In September of 2020, there are more than 3,000 cryptocurrencies in operation. However, there is an extensive problem of the potential data breach, data abuse, or misuse. In such environments, due to the complicated nature of the interactions and sophisticated information diffusion schemes within the systems. Recognizing this problem, recently, new regulation and amendments aiming to better protection of the user information and rights of data subjects have been introduced. One of the significant schemes is the European General Data Protection, GDPR, which became law in May of 2018 and applies to any organization that interact data subjects based in the European Union. Thank you so much, everyone, for your attention, and I hope this presentation will have served to understand better the crypto world. See you later.